Degenerate matter and Fermi-Dirac statistics. This is a topic of discussion in today's lecture. Here, degenerate matter means you would find this topic in the field of astrophysics, more specifically in the field of stellar physics. Okay, so in the study of stellar physics, you would find this topic, degenerate matter. Here, matter is not found in usual condition or in normal condition. Instead, the condition is somewhat abnormal because here density is so much high as 1 billion ton, more than 1 billion ton per cubic, 1 billion ton per cubic meter, right? Again, as high as you would get 10 to the power 17 kg per cubic meter. That much density exists in case of degenerate matter. Okay, so this is nothing but the study of astrophysics. So, question is, what is degenerate matter and where you would find this matter? Okay, so during the study of Fermi-Dirac statistics, you know that the particles fermions means electrons, protons, neutrons, these are known as fermions. Particles with half integer spin are called fermions, and these fermions obey Pauli Exclusion Principle. You know Pauli Exclusion Principle. No two fermions can occupy the same quantum state. That is Pauli Exclusion Principle. And the particles which obey Fermi-Dirac statistics must obey Pauli Exclusion Principle. Actually, Fermi-Dirac statistics is applicable only for the particles which obey Pauli Exclusion Principle, right? So here we are talking about white dwarfs and neutron stars. At the end of the life cycle of stars, you would get three types of things in space. One is white dwarf, another one is neutron star, and the third one is black hole, right? So first let us talk about a white dwarf. If the mass of the star is less than 1.4 times than that of the sun, our sun, okay? And that limit is called the Chandrasekhar limit. So in that case, the end life of any star, means end stage of any star is nothing but a white dwarf. In the formation of white dwarf, what happens? It sheds the outer layers, and the remnants of the star, of the dead star, okay, is called white dwarf. Here there is enormous gravitational pull. Gravitational force is enormous. Still, the remnant does not squeeze into a point, or does not squeeze into a very small volume, because due to degeneracy pressure, due to the presence of degenerate matter, degeneracy pressure generates, and this degeneracy pressure restricts or counters the effect of gravitational pull. So there is a balance between degeneracy pressure and the gravitational pull. Okay, and that remnant of the dead star is called white dwarf. Here you would find only electrons, not neutrons, only electrons. Means majority of the particles in a white dwarf are nothing but electrons, and electrons are fermions. Okay, so they must obey Pauli Exclusion Principle, and they must obey Fermi-Dirac statistics. Okay, since these electrons are creating degeneracy pressure, that's why there is a balance between the gravitational pull and degeneracy pressure, and you would get the end result as a white dwarf. Okay, and in case of neutron star, this happens at the end of the life cycle of massive stars. Okay, that means here Chandrasekhar, the value means the mass of that massive star is maybe millions times or billions times more than that of our sun. Okay, and at the end of the life cycle of those stars, the result is either a neutron star or a black hole. Okay, so we are not talking about black hole here in this lecture. We are talking about only neutron star. In case of neutron star, initially there should be the presence of electrons and protons, but due to huge gravitational pull, due to the presence of huge gravitational force, electrons and protons combine together and form only neutrons. So majority of the particles found in neutron stars are neutrons, and that's why the name is given neutron star, because majority of the particles are neutrons. And here also same thing, degeneracy pressure is created. Okay, why this pressure is created? Because here in case of white dwarfs, electrons, and in case of neutron stars, neutrons, they do not behave classically. Instead, quantum mechanical effects become predominant. They play the dominating role. They means here quantum mechanical effects. Okay, and due to this, degeneracy pressure is nothing but the effect of degeneracy pressure is the result of quantum mechanical effects present in the neutrons in case of neutron star and in the electrons in case of white dwarfs. Okay, so this study is required to know the white dwarfs, to know the neutron stars in detail. Okay. Anyway, so this discussion is nothing but the application of Fermi-Dirac statistics. Okay, and yes, I have finished discussing about the topic degenerate matter. So degenerate matter is, no doubt it is matter. Practical evidence is there. It is matter, but you would get unusual behavior of the matter, because here classical behavior wouldn't be observed, only quantum mechanical effects are observed in case of degenerate matter, and here the density is very high. In case of white dwarfs, the density ranges from 10 to the power 9 to 10 to the power 10 kg per cubic meter. That means from 1 billion to 10 billion kg per cubic meter. And in case of neutron star, the density is even higher, and that value is almost around 10 to the power 17, 10 to the power 17 kg per cubic meter. So extremely high density of matter is observed in case of this state, which is known as degenerate matter. And it is found in white dwarfs as well as in neutron stars. Okay, so this was all about today's topic, and this is the end of this video. Thank you for watching this video.